What if everything you thought you knew about the universe was flipped inside out the moment you crossed the edge of a black hole? These cosmic monsters don't just swallow light, they twist the very fabric of reality, warping space and time into something unrecognizable. Today, we're venturing beyond the event horizon to uncover the secrets hidden in the heart of a black hole. From the crushing grip of the singularity to the mind-bending theories about what lies beyond, we'll explore the science that challenges our understanding of physics itself. Strap in, this journey doesn't just bend the rules, it shatters them. Let's rewind the cosmic clock to where every black hole begins, not with a bang, but with the dramatic final act of a dying star. Picture a star at least 20 times more massive than our Sun, burning through its fuel at an astonishing rate. For millions of years, it fuses elements in its core, building heavier and heavier atoms like a cosmic factory. But when the star runs out of fuel, the delicate balance between gravity pulling inward and radiation pushing outward collapses literally. In an instant, gravity wins. The star's core implodes under its own weight, triggering a cataclysmic explosion called a supernova, one of the most violent events in the universe. For a brief moment, it outshines entire galaxies. But what's left behind depends on the star's original size. If the core remnants are between about 1.4 and 3 times the mass of our Sun, they crumple into a neutron star, a city-sized object so dense a teaspoon of it would weigh 1 billion tons. But if the core is even heavier, something far stranger happens. Gravity becomes unstoppable, crushing matter down to an infinitely tiny point, a singularity. This is where the rules of physics as we know them break down. Space and time become so warped that not even light can escape, creating an event horizon, a point of no return. But black holes aren't always born from supernova. Some emerge silently when supermassive clouds of gas collapse directly under gravity's pull, skipping the explosion entirely. These monsters can weigh millions or even billions of times the mass of our Sun, lurking at the centers of galaxies like ours. The terrifying beauty of black holes isn't just in their destructive power, it's in the way they reveal the raw forces shaping the universe itself. From the ashes of dead stars, they rewrite the laws of reality, and we've only just begun to understand how. Crossing the event horizon is like stepping over the edge of a waterfall, only instead of water pulling you down, it's the fabric of space itself. This invisible boundary marks the moment gravity's grip becomes absolute. No signal, no light, no desperate SOS could ever make it back out. The universe outside simply vanishes. Think of space as a flowing river. Far from the black hole, the current is gentle. You could swim against it if you had enough strength. But as you drift closer, the current speeds up, tugging harder. The event horizon is where the river turns into a raging waterfall. No matter how fast you paddle, the pull becomes unstoppable. Past this point, every path leads inward, warped so severely that even if you somehow turned around, you wouldn't be moving away, you'd just be falling toward the center at a different angle. Here's the twist: from your perspective, nothing would feel unusual at first. No sudden jolt, no dramatic warning sign. But to an outside observer watching you approach the event horizon, time itself would seem to distort. You'd appear to slow down, freezing in place like a glitching hologram, your image fading into redshifted nothingness. That's because light struggling to escape gets stretched to longer, redder wavelengths, a ghostly farewell signal before you slip beyond the observable universe. Black holes don't just trap objects, they trap information. Every atom, every bit of energy that crosses that threshold takes its secrets with it, sparking one of physics' greatest paradoxes. But that's a mystery for another chapter. For now, remember this: the event horizon isn't a physical wall, it's the universe's ultimate one-way door, and what lies beyond. That's where things get truly bizarre. Past the event horizon, gravity takes on a grotesque new form. One that doesn't just pull you in, but stretches you like cosmic taffy. This is spaghettification, a gruesomely playful term for an utterly violent process. Imagine dangling your feet toward a black hole. Gravity's pull is so much stronger at your toes than your head that the difference becomes deadly. Picture gripping a rubber band at both ends and yanking it apart. Only instead of elastic, it's your body. Tidal forces, the same ones behind Earth's ocean tides but amplified to nightmare extremes, turn anything unlucky enough to drift too close into a streaming filament of atoms. A human would be elongated into a strand miles long before inevitably snapping apart. Even stars aren't spared. Astronomers have watched as black holes rip gas giants apart in real time, their material twisting into luminous spirals before vanishing. The physics behind this is surprisingly simple. Gravity obeys an inverse square law. Double your distance from a mass and its gravitational tug weakens by a factor of 4. Near a black hole's singularity, the difference in pull between your head and feet could be millions of times stronger a cosmic tug of war no material can withstand. But here's the surreal part, you wouldn't necessarily feel it happening. In smaller black holes where the event horizon sits close to the singularity, tidal forces spike so abruptly that spaghettification occurs before crossing the threshold. But in supermassive black holes like the one at our galaxy's center, their event horizons are so wide you could drift deep inside before the stretching begins. By then, of course, escape was never an option. This isn't just theoretical horror. In 2019, astronomers witnessed a star suffering this fate 375 million light-years away. As it was shredded, its debris blazed at temperatures over 30,000 degrees, a fleeting beacon marking where space-time itself becomes a funhouse mirror. So while black holes won't actually serve you as cosmic pasta, they will remind you, the universe has far stranger recipes than we could ever cook up. At the moment you slip past the event horizon, something unsettling happens. The universe as you knew it stops making sense. Directions reverse, time warps. The concept of away ceases to exist. No force in nature could propel you back out, not because the black hole is pulling you in, but because space itself is falling inward faster than the speed of light. Think of it like standing on an escalator moving upward, only this escalator is plunging downward so fast that even if you sprinted at full speed, you'd still descend. Inside the event horizon, every step you take, every breath, every heartbeat carries you inexorably closer to the singularity. There's no standing still, no pausing for reflection. Space here isn't just curved, it's flowing, dragging everything with it in a current that only runs one way. And then there's time, or rather, the eerie way it distorts. Outside the black hole, time ticks forward predictably. But beyond the horizon, time and space swap roles. Instead of moving through time toward the future, you're funneled through space toward the singularity, as unavoidably as a leaf swept downstream. What feels like minutes to you might be centuries for someone watching from afar, their view of you frozen at the threshold as light struggles to escape the hole's grip. Yet here's the strangest part, despite the chaos, you wouldn't feel any sudden jolt or turbulence. The laws of physics still apply locally, at least until tidal forces take over. You could float weightlessly, sipping imaginary tea in your doomed spaceship, oblivious to the fact that every possible path now leads to a single, inescapable destination. This is the black hole's cruelest trick. It doesn't announce its horrors with fireworks or alarms. It lulls you into a false sense of normalcy, even as the universe's rulebook quietly burns behind you. And ahead, only the singularity waits, a place where physics surrenders entirely. But that's a nightmare for another moment. For now, just remember, once you cross that line, the universe as you know it isn't just left behind, it's rewritten. Deep inside every black hole, beyond the event horizon and past the stretching tides of spaghettification, lies the ultimate cosmic enigma, the singularity. This isn't just the end of the road, it's the point where the road itself disintegrates. The singularity is where the known laws of physics collapse under the weight of their own contradictions, leaving us with an equation that reads, infinity equals chaos. At its core, a singularity is a place where matter gets crushed into an unimaginably small point. So small, in fact, it occupies zero volume. Think of it like compressing the entire mass of a star or even a galaxy into something smaller than a single atom. The result, infinite density, a term so extreme that even physicists struggle to picture it. Gravity here doesn't just bend space-time, it snaps it like a twig. The numbers in our equations explode into nonsensical infinities, a glaring sign that our theories are missing something fundamental. Most of us are familiar with Einstein's theory of general relativity, which describes gravity as the curvature of space-time. It's brilliant until you reach a singularity. Here, the equations spit out nonsense, predicting an infinitely dense point where time and space cease to function as we know them. Quantum mechanics, the other pillar of modern physics, doesn't fare much better. At these scales, the tiny, unpredictable jitters of quantum particles should matter. But we have no theory yet that can marry these two worlds in such extreme conditions. Some scientists argue that singularities might not be infinitely small after all. Loop quantum gravity, a theory attempting to unify relativity and quantum mechanics, suggests space-time might be granular, like a fabric woven from tiny, indivisible threads. If true, there could be a smallest possible scale where collapse simply stops, preventing infinite density. Others propose that black holes might not even have singularities in the traditional sense. Instead, they might hide exotic objects like Planck stars, ultra-dense remnants where matter rebounds from collapse like a cosmic spring, but the most unsettling idea. That singularities could be gateways. Some interpretations of the math hint that they might puncture space-time, creating tunnels to other universes or distant corners of our own. Of course, no information could ever come back to confirm that, assuming you could even survive the journey. For now, the singularity remains the ultimate blind spot in our understanding of the cosmos. It's a mathematical storm where logic drowns, and yet, unlocking its secrets might finally reveal the deeper rules governing reality itself. One thing's certain, if you ever found yourself staring into that abyss, you wouldn't just be witnessing the death of physics, you'd be glimpsing the birth of something entirely new. At the heart of every black hole's mystery lies a fundamental clash, a cosmic tug-of-war between two of physics' greatest theories. On one side, Einstein's general relativity paints a haunting picture, a singularity where space and time cease to exist as we know them. On the other, quantum mechanics, the rulebook for the subatomic world, insists that nature abhors such infinities. The result, a battle of ideas so intense it could rewrite our understanding of reality itself. General relativity describes gravity as the curvature of space-time. Massive objects like stars and planets dent the cosmic fabric like a bowling ball on a trampoline. Near a black hole, this curvature becomes so extreme that the trampoline rips, plunging into an infinitely deep pit, the singularity. But here's the catch. Relativity treats space and time as smooth, continuous surfaces, an elegant idea that works perfectly until you reach subatomic scales. Enter quantum mechanics. At the tiniest levels, the universe isn't smooth at all. It's a chaotic, flickering foam where particles pop in and out of existence, and certainty dissolves into probability. Quantum rules forbid anything from being infinitely small or dense, meaning the singularity, as relativity predicts, shouldn't exist. The math simply implodes, like two languages trying to shout over each other without a translator. This isn't just an academic disagreement, it's a crisis. Black holes are the only places in the universe where both theories must apply simultaneously, where the immense gravity of general relativity meets the quantum weirdness of the microscopic. Yet when forced together, they produce nonsense. Some physicists propose a fix, quantum gravity, a yet undiscovered framework that might reconcile the two. Imagine stitching the trampoline's fabric with threads so fine they account for every tiny quantum ripple. Theories like string theory or loop quantum gravity attempt this, suggesting space-time might be woven from discrete, indivisible chunks, preventing infinite collapse. Others speculate that singularities could be replaced by exotic quantum objects like fuzzballs or wormholes, where matter doesn't vanish but gets smeared across hidden dimensions. But until we crack this puzzle, black holes remain the ultimate testing ground for physics. They're cosmic laboratories where the universe forces us to confront the limits of our knowledge, and perhaps, if we're lucky, the first glimpses of what lies beyond it. Here's the next segment of the script, maintaining the flow from previous sections while diving into the information paradox. If black holes truly destroy everything they consume, they might be erasing something far more precious than matter. They could be deleting the universe's history itself. This is the heart of Stephen Hawking's infamous black hole information paradox, a puzzle so profound it shook the foundations of physics. Here's the problem: quantum mechanics, the rulebook for how particles behave, has one ironclad law: information cannot be destroyed. Every particle interaction, every collision leaves a trail. Even if you burn a book, in theory, the smoke and ash still hold clues to reconstruct its pages. The universe remembers, but black holes seem to break this rule. When matter vanishes past the event horizon, all traces of its original state, its information, appear lost forever, crushed into the singularity's unknowable depths. Hawking first exposed this paradox in the 1970s by combining relativity with quantum theory in a way no one had before. His calculations suggested black holes don't just trap matter, they evaporate over eons, leaking energy in the form of faint radiation, now called Hawking radiation. But here's the catch: that radiation seemed completely random, carrying no fingerprints of what fell in. If a black hole eventually vanishes, leaving only this featureless glow, where did the original information go? The implications are staggering. If information can vanish, the entire framework of quantum mechanics, the science behind everything from atoms to computers, would need rewriting. Physicists split into warring camps. Some, like Hawking initially, argued information was destroyed, even calling for quantum textbooks to be revised. Others, like Leonard Susskind, fought back, declaring, "The universe is not a courtroom where evidence can disappear." The debate raged for decades until a potential solution emerged, one that turns black holes into cosmic holograms. The idea: information isn't inside the black hole, it's smeared across its event horizon like a scrambled projection. Just as a two-dimensional DVD encodes a three-dimensional movie, the surface of a black hole might hold all the data of what fell in, encoded in vanishingly small ripples. When Hawking radiation escapes, it could theoretically carry that information back out, pixel by pixel, just in a form we can't yet decode. In the end, Hawking himself conceded. In 2004, he admitted information might escape after all, settling the debate sort of. The math suggests a way out, but how it happens remains one of physics' greatest open questions. One thing's clear: black holes aren't just cosmic trash compactors. They're mirrors, forcing us to confront whether the universe truly forgets, or if we just don't yet speak its language. This segment avoids repetition by opening with a bold conceptual stakes: erasing history vs. destroying matter, varying sentence structure, mixing concise explanations. Here's the problem: with vivid metaphors, cosmic holograms, presenting multiple perspectives, Hawking vs. Susskind, initial vs. revised theories, ending on a forward-looking note: the unresolved how, without rehashing prior points, keeping tone authoritative but conversational. One thing's clear. Let me know if you'd like any refinements. There's a cosmic irony at work here: black holes, the universe's ultimate vaults, might not be so secure after all. Thanks to a quantum quirk, these cosmic predators don't just consume, they leak. This phenomenon, known as Hawking radiation, reveals something startling. given enough time, even the mightiest black hole could fade into nothingness. The secret lies in empty space, or rather, what we think is empty. Quantum physics tells us the vacuum isn't truly vacant. Instead, it's a seething sea of virtual particles, pairs of particles and antiparticles that constantly wink in and out of existence, borrowing energy from the universe before annihilating each other in a flash. Normally, this dance goes unnoticed, but near a black hole's event horizon, gravity warps the rules. Picture one of these particle pairs appearing right at the edge. If gravity's pull separates them before they can collide, something eerie happens. One particle falls in, while the other escapes, stealing a tiny bit of the black hole's energy in the process. To an outside observer, it looks like the black hole just emitted radiation. Over eons, this slow trickle adds up, causing the black hole to lose mass. Smaller black holes radiate faster, their final moments resembling a firework, a burst of energy as they blink out of existence. Supermassive ones, they'd take longer to evaporate than the current age of the universe. Hawking's calculations sent shockwaves through physics because they hinted at a startling truth. Black holes aren't eternal. They have a lifespan, one dictated by quantum mechanics' subatomic whispers. But here's the twist. This radiation appears totally random, a thermal hiss with no trace of what fell in. That's what sparked the information paradox. If the radiation carries no data, does the black hole truly erase the past? Recent theories suggest otherwise. The radiation might seem random, but like a scrambled radio signal, its chaos could hide intricate patterns. A cosmic encryption of everything the black hole ever consumed. Decoding it would be like reconstructing a burned book from the ashes, but the math hints it's possible. So while black holes might fade, their secrets could linger, imprinted on the fabric of spacetime itself. They're not just monsters in the dark, they're puzzles, challenging us to listen more closely to the universe's quietest whispers. The universe has a way of hiding its deepest symmetries in plain sight, and nowhere is this more baffling than when thermodynamics, the science of heat and energy, collides with the monstrous gravity of black holes. At first glance, these cosmic vacuum cleaners seem like the opposite of anything governed by familiar laws like temperature or entropy. Yet somehow, they obey rules eerily similar to those describing steam engines and melting ice. Let's start with entropy, a measure of chaos or disorder in a system. A shattered cup has higher entropy than an intact one, scattered papers more than a neatly stacked pile. In the 1970s, physicist Jacob Bekenstein made a radical proposal. Black holes, those perfect traps of order and darkness, must also carry entropy. In fact, their entropy isn't just non-zero, it's colossal, proportional to the area of their event horizons. Imagine scribbling the universe's messiest diary onto a surface smaller than a pinpoint, yet containing more hidden information than all the books ever written. This wasn't just poetic thinking. Bekenstein's math revealed something profound. Black holes might be the ultimate entropy sinks, gathering the disorder of everything they consume. And where there's entropy, thermodynamics insists there must also be temperature. At the time, this seemed absurd. How could a pitch-black void, sucking in all light and energy, have a temperature? Enter Stephen Hawking. His calculations showed that when quantum effects dance at a black hole's edge, they produce exactly that, a faint thermal glow, now known as Hawking radiation. Here's where the analogy gets surreal. Black holes behave like cosmic refrigerators running in reverse. Normally, heat flows from hot to cold until equilibrium is reached. But a black hole's event horizon creates a temperature gradient, warmer outside, colder inside, sucking entropy inward like a whirlpool devouring debris. This bizarre thermodynamics even gives black holes a heat capacity, meaning they can absorb energy without necessarily heating up. Yet the most startling parallel lies in black hole mechanics. Just as the laws of thermodynamics forbid perpetual motion machines, black holes obey their own set of no-go rules. angular momentum, electric charge, and mass are conserved, mirroring how energy and entropy balance in a closed system. It's as if the universe encoded its deepest operating manual twice, once for the quantum world, and again in the warped spacetime of black holes. So next time you watch steam rise from your coffee, remember, the same physics governing that swirling heat might also hold the key to understanding the darkest objects in existence. Black holes don't just bend spacetime, they whisper secrets about how chaos and order intertwine across the cosmos. But what if singularities, those infinitely dense, physics-breaking points at the heart of black holes, don't actually exist? Some physicists argue nature might have a more elegant solution, one that sidesteps the mess of infinities altogether. Enter Planck stars and gravastars, exotic cosmic objects that rewrite the black hole's final act without tearing apart the rulebook of reality. Take Planck stars first. Imagine a collapsing star doesn't just keep shrinking forever, but instead hits a wall, a limit so small it's governed by the Planck length, the shortest possible distance in quantum physics. At this scale, the star's core would rebound like a compressed spring, creating an ultra-dense object with finite density rather than infinite. The catch: we'd never see the bounce from outside. Due to time dilation near the event horizon, the rebound would appear frozen, stretching across billions of years. To distant observers, it would still look like a classic black hole, just with a cosmic sleight of hand hiding its true nature. Then there are gravastars, short for gravitational vacuum stars. These theoretical oddities ditch singularities entirely, replacing them with a bizarre bubble of spacetime. Picture a black hole's event horizon not as a point of no return, but as a shell enclosing a pocket of dark energy, the same mysterious force accelerating the universe's expansion. Inside, space would be eerily empty, with gravity and quantum forces perfectly balanced to prevent collapse. Outside, nearly indistinguishable from a traditional black hole. The difference: no singularity means no information paradox, no infinite densities, just a strange, stable alternative that keeps physics intact. Not all ideas are equally accepted, of course. Some critics argue these theories introduce unnecessary complexity compared to singularities, even if those singularities break our equations. Others counter that nature abhors infinities, and that when our math predicts them, it's usually a sign we're missing a deeper truth. The beauty of these alternatives isn't just in their creativity. They're stress tests for our understanding, forcing us to ask, is the singularity a real physical object, or just a placeholder for something we haven't discovered yet? Until we can peer past an event horizon, or until a brilliant experiment proves otherwise, black holes will keep their secrets close. But one thing's certain: the universe rarely resorts to true chaos. Beneath the apparent madness, there's usually order waiting to be found. The universe has a funny way of recycling itself, even in the most extreme places. If loop quantum gravity is right, the crushing heart of a black hole might not mark the end of space and time, but the beginning of something entirely new. Forget the singularity's infinite density. This radical theory proposes that gravity's pull could reach a breaking point, triggering a cosmic rebound that births a whole new universe. Loop quantum gravity, a leading contender in the quest to unify relativity and quantum mechanics, suggests spacetime isn't smooth and continuous. Instead, it's woven from tiny, indivisible threads like a fabric with a finest possible stitch. At microscopic scales, these threads resist further compression, creating a force that counteracts gravity's crush. Picture squeezing a spring. Once it hits its limit, it pushes back. In this scenario, a collapsing black hole wouldn't vanish into a singularity. It would rebound, exploding outward in a fiery reset, a big bang in reverse. Here's where it gets wild. Some models suggest this rebound doesn't just happen inside the black hole. It might spawn an entirely separate spacetime, hidden behind the event horizon. Our universe, in this view, could itself be the aftermath of a black hole bounce from another cosmos. It's like a cosmic Russian doll, each black hole harboring a new universe within, each with its own physics, stars, and possibly even its own black holes nesting further realities. Not everyone's convinced, of course. Critics argue this idea is speculative, lacking observational proof, but supporters point to tantalizing clues. The uniformity of our own universe's early expansion, for instance, aligns suspiciously well with what such a bounce might produce. And if these baby universes inherit properties from their parent black holes, it could explain deeper mysteries like why our cosmos seems finely tuned for life. Whether or not black holes truly hide budding universes, the real takeaway is this: the darkest corners of existence might not be dead ends but crossroads. And if loop quantum gravity is onto something, the universe's greatest monsters could also be its most creative architects. After all, nature rarely wastes anything, not even a catastrophe. Imagine a black hole not as a bottomless pit, but as a tangled knot of cosmic yarn, a dense, vibrating ball of energy where every atom's fate is written in loops of spacetime itself. This isn't science fiction, it's string theory's bold reimagining of black holes, fuzzballs. Forget the crushing singularity. These theoretical objects replace the infinite with something far stranger, yet oddly familiar. String theory suggests the universe's building blocks aren't point-like particles but tiny, vibrating strings. When this idea applies to black holes, the result is a fuzzball, a massive, knot-like structure where strings twist and buzz at the event horizon, filling the entire volume a singularity would occupy. No empty space, no infinite density, just an intricate web of energy so compact it mimics a black hole's gravity. Here's the kicker: fuzzballs solve two headaches at once. First, they erase the need for singularities, those pesky infinities where physics breaks down. Instead of collapsing into a point, matter gets smeared across the fuzzball's surface, like ink dissolving into a sponge. Second, they sidestep the information paradox. Since strings store data in their vibrations, everything swallowed by the black hole lingers encoded in its fuzz, no cosmic amnesia required. Critics argue fuzzballs lack experimental proof, but supporters fire back with elegance. If black holes are fuzzballs, their event horizons wouldn't be featureless. Microscopic bumps and jitters could imprint on Hawking radiation, leaving faint fingerprints of what fell in. It's a long shot to detect, but not impossible, like hearing a symphony in static if you know the right tune to listen for. What makes this idea thrilling isn't just its audacity, but its humility. Maybe the universe doesn't rely on monstrous singularities. Maybe, at its most extreme, it simply ties up loose ends literally. Whether fuzzballs are real or just a beautiful detour, they remind us the universe's darkest corners might be its most creative classrooms. What if black holes had cosmic counterparts, not just consuming matter but spitting it back out? Enter white holes, the theoretical yin to a black hole's yang. While black holes pull everything past a point of no return, white holes would do the exact opposite, violently repel anything that comes near, forbidding entry entirely. It's like a reverse cosmic vacuum, one that blasts rather than sucks. Einstein's equations allow for white holes to exist, though we've never spotted one. They emerge as mathematical mirror images of black holes, seemingly flipping the rules. Picture a black hole's event horizon, but working in reverse. Instead of matter vanishing forever, it's ejected violently outward in a fountain of energy and particles. Some theories even suggest a white hole could be the other end of a black hole's tunnel, an exit point for whatever fell in. But here's where it gets speculative. If black holes truly connect to white holes via wormhole shortcuts through spacetime, could they serve as cosmic recycling plants? Matter disappears into a black hole in one part of the universe, only to erupt from a white hole somewhere else or even in another time. It's a tantalizing idea, one that turns black holes from dead ends into cosmic turnstiles. Not everyone's convinced. Critics argue that white holes violate the second law of thermodynamics, creating order from chaos without a clear energy source. Others counter that if they exist at all, white holes would be incredibly short-lived, collapsing instantly under their own instability. Then there's the observational problem. If white holes spew matter out, why haven't we seen one? Some physicists speculate that gamma-ray bursts, the most energetic explosions in the universe, could be white holes blinking into existence before vanishing. Whether real or just a quirk of math, white holes force us to question our assumptions. If they're out there, they could rewrite our understanding of cosmic evolution, where nothing is truly destroyed, just relocated. And if not, they're still a brilliant reminder that the universe's rulebook might have pages we haven't even glimpsed yet. Some of the wildest ideas in physics start with a simple question: what's on the other side? If black holes are cosmic dead ends, the universe feels like a one-way street, but wormholes flip that script entirely. Imagine a tunnel burrowing through the fabric of space-time, stitching two distant points together like a hidden seam in reality. One entrance could hover near Earth while the other dangles light years away, or even in another time. The math behind this isn't science fiction. Einstein's equations actually allow for such shortcuts, known as traversable wormholes. Picture folding a sheet of paper so two dots touch. A wormhole is the pen stroke that skips the distance between them. Black holes might serve as one mouth of this tunnel, their immense gravity warping spacetime enough to pry open a passage. The catch: stability. Without some exotic material like negative energy to prop the throat open, these bridges would snap shut faster than you could blink, crushing anything foolish enough to enter. Negative energy sounds like fantasy, but quantum mechanics offers a glimmer of hope. The Casimir effect, where two metal plates in a vacuum experience an attractive force, hints that negative energy densities might exist in nature. If scaled up, could this exotic physics stabilize a wormhole long enough to traverse? Maybe, but don't pack your interstellar suitcase yet. The energy required could dwarf the output of entire stars, and one wrong calculation might leave you spaghettified mid-journey. Here's where things get trippier. Wormholes don't just bend space, they twist time. If one end moved near a black hole's event horizon where time crawls and the other stayed in open space, you could theoretically step through and arrive before you left. That's a time machine woven into the cosmos itself. No wonder physicists like Kip Thorne have spent decades untangling whether these shortcuts could exist without triggering paradoxes like going back to prevent your own birth. Of course, skeptics abound. Wormholes may be mathematically possible, but nature has a way of slamming doors on shortcuts. Quantum effects might destabilize them instantly, or the universe might forbid time travel to preserve causality. Yet, even as a thought experiment, wormholes force us to confront a thrilling idea. The cosmos might be far more connected and far stranger than we ever dared to dream. And if they do exist, well, the universe just handed us the ultimate cheat code. Time doesn't just slow down near a black hole, it drags, warping into a sluggish crawl the way syrup drips from a spoon. This is Einstein's time dilation in its most extreme form, where gravity so intense it bends light also stretches seconds into years. Picture the crew from Interstellar landing on Miller's planet, where every hour spent in the black hole's grip costs them 7 years back home. That's not Hollywood exaggeration, it's real physics dialed up to 11. The closer you get to the event horizon, the more space-time twists like taffy. To an outside observer, your movements would appear to freeze, your signals stretching into distorted, fading echoes. But here's the surreal part: you wouldn't feel a thing. Time would pass normally in your own frame of reference until you glanced up and realized the universe outside had fast-forwarded centuries without you. This isn't just theory. GPS satellites orbiting Earth actually account for tiny time dilation effects, adjusting their clocks because gravity weakens ever so slightly at higher altitudes. Near a black hole, though, the effect isn't measured in nanoseconds. A single orbit could mean watching civilizations rise and fall from afar. The math behind it hinges on relativity's core idea. Gravity doesn't just pull objects, it warps the very fabric of time itself. So why does this happen? Think of space-time as a trampoline. Place a bowling ball in the center and the fabric dips steeply. Roll a marble near the edge and its path bends inward. That's gravity. But if the marble could experience time, it would tick slower the deeper it rolled into the dip. A black hole's dip is so extreme that time near the edge effectively grinds to a halt relative to the flat spacetime far away. The takeaway: black holes don't just trap matter, they imprison time, turning what should be a universal constant into a flexible, personal experience. One astronaut's coffee break could be another's lifetime, and if that doesn't make you question the nature of reality, just wait, there's more where that came from. The event horizon has always been described as a silent, invisible boundary, a place where space flows smoothly past the point of no return. But what if crossing it wasn't as uneventful as we thought? What if, instead of slipping quietly into darkness, you were vaporized in an instant by a wall of searing energy? This isn't science fiction, it's the infamous firewall paradox, a debate so intense it's divided physicists for over a decade. At the heart of the controversy is a clash between two fundamental principles. On one hand, Einstein's general relativity tells us the event horizon should feel like nothing special, no sudden jolt, no dramatic warning signs, but quantum mechanics, the rulebook for particles and atoms, suggests something far more violent. When black holes emit Hawking radiation, the escaping particles should leave behind a blistering layer of energy right at the horizon, a firewall hot enough to obliterate anything that touches it. The implications are staggering. If firewalls exist, they'd rewrite our understanding of black holes overnight. No more smooth descent into the unknown, just an abrupt, fiery end. But here's the catch. This idea contradicts relativity's prediction that free-falling observers should experience nothing unusual at the horizon. It's like claiming you can walk through a door and be incinerated, while someone watching from outside insists the door was perfectly safe. Supporters of the firewall, like physicists Ahmed Olmary and Joseph Polchinski, argue it's the only way to resolve the information paradox. If information isn't lost inside the black hole, maybe it's burned away at the boundary, preserving quantum laws at the cost of relativity's elegance. Critics, however, call it an overcorrection, a violation of Einstein's equivalence principle, which states that free-falling frames should feel no extreme forces. Leonard Susskind famously compared it to throwing the baby out with the bathwater, suggesting there must be a subtler solution. The debate isn't just academic. It forces us to confront whether our theories can coexist, or if black holes are exposing a flaw in our deepest understanding of reality. Some researchers propose loopholes like fuzzballs or quantum hair that might smooth out the contradiction. Others speculate firewalls could form just inside the horizon, sparing infalling observers while still scrambling information. For now, the firewall remains a specter at the edge of physics, a paradox as hot as the phenomenon it describes. Whether it's real or not, one thing's clear: black holes aren't just swallowing matter. They're forcing us to question whether the universe plays by consistent rules, or if, at its most extreme, reality itself has a temper. Somewhere between the fiery chaos of the firewall paradox and the smooth predictions of general relativity, there's a tantalizing third option, one where black holes aren't bald but hairy. Not in the literal sense, of course. The quantum hair hypothesis suggests these cosmic monsters might carry subtle, quantum-scale imprints of everything they've ever consumed, like a fingerprint etched into the fabric of spacetime itself. For decades, physicists clung to the no-hair theorem, the idea that black holes could be described by just three simple traits: mass, spin, and charge. Everything else, the type of matter, its arrangement, even whether it was made of pianos or protons, would be erased forever. But quantum hair flips this notion on its head. Imagine tossing a book into a black hole. Instead of vanishing into featureless oblivion, the information within might leave faint vibrational patterns on the event horizon, like ripples frozen in place. These quantum waves wouldn't just be random noise, they'd encode the very essence of what fell in. The math behind this is elegant yet complex. Just as a violin string vibrates at specific frequencies to produce distinct notes, quantum fields near a black hole's surface could resonate in unique ways, storing data in their oscillations. Unlike Hawking radiation's scrambled thermal hiss, this hair would preserve information in a structured, retrievable form, no paradox required. Critics argue that detecting such delicate imprints borders on fantasy. Even light struggles to escape a black hole's pull, let alone subtle quantum signals, but proponents counter that future gravitational wave observatories, with their unprecedented sensitivity, might one day pick up these whispers. If they succeed, it would confirm one of the most profound ideas in modern physics, that nothing in the universe is truly forgotten, not even by its darkest inhabitants. What makes this theory so compelling isn't just its potential to solve the information paradox. It's the poetic symmetry. Black holes, long seen as the ultimate erasers, might actually be cosmic archivists engraving history onto the very boundaries that seem to erase it. The universe, it seems, has a way of keeping receipts. What if everything that falls into a black hole, every atom, every shred of starlight, gets imprinted on its surface like a tattoo on cosmic skin? This is the essence of the holographic principle, one of the most mind-bending ideas in modern physics. It suggests that the three-dimensional chaos inside a black hole might be perfectly mirrored on its two-dimensional event horizon, like a movie projected onto a screen. Here's how it works. In the everyday world, we're used to information having volume. A book has pages, a hard drive has layers, but black holes challenge this intuition. When matter crosses the event horizon, it doesn't just vanish. According to quantum mechanics, its information must persist somewhere. The holographic principle proposes that this data isn't lost in the abyss but gets painted onto the black hole's surface in vanishingly tiny pixels, each no larger than a Planck length, the smallest possible unit of space. Think of it like a holographic sticker. At first glance, it looks flat, but tilt it under light and a 3D image emerges. Similarly, the surface of a black hole could encode all the complexity of its interior through intricate quantum patterns. Even stranger, this isn't just a black hole quirk. Some theorists argue the entire universe might operate like this, with gravity and dimensionality emerging from a hidden, lower-dimensional code. The math behind this idea is both elegant and bizarre. Just as a symphony can be compressed into grooves on a vinyl record, the holographic principle suggests space-time itself might be a projection. Black holes, with their stark boundaries and extreme gravity, are the perfect testing ground. Their event horizons could act like cosmic hard drives, storing information in vibrations akin to the ones on a violin string, subtle but rich with meaning. Critics question how such a radical compression could work without distortion, while supporters point to breakthroughs in string theory and quantum gravity that hint at its plausibility. If true, it would mean that the universe's most mysterious objects aren't just destroyers, they're cosmic archivists, etching history onto the very surface that seems to erase it. After all, nature rarely wastes anything, not even a single bit of information. What's thrilling isn't just solving the black hole information paradox. It's the possibility that we're glimpsing a deeper truth. Reality might not be as three-dimensional as it seems. The universe, it turns out, could be running on a hidden layer, a cosmic operating system we're only beginning to decode. At first glance, black holes seem like the ultimate cosmic shredders, objects so destructive they erase everything they touch. Yet beneath their terrifying reputation lies a startling truth. These gravitational monsters might be the universe's most meticulous librarians. The key to this paradox, entropy, a concept we usually associate with disorder, but which takes on an almost poetic meaning when applied to black holes. Entropy isn't just about chaos, it's about hidden information. Think of a messy desk, papers scattered everywhere seem random, but each sheet still holds its original content. In physics, entropy measures how much information is hidden by a system's disorder. A hot cup of coffee cooling to room temperature, for example, spreads its energy in a way that looks random, but the underlying microscopic details are still there, just harder to read. Now imagine scaling this up to a black hole. In the 1970s, Jacob Bekenstein made a radical leap. What if black holes, those perfect vacuums of darkness, carry entropy too? His calculations revealed something mind-blowing. A black hole's entropy isn't just non-zero. It's colossal, proportional to the area of its event horizon. The bigger the black hole, the more information it can hide. To put it in perspective, a single stellar mass black hole could hold more entropy than all the particles in the observable universe combined. This revelation reshaped physics overnight. If black holes have entropy, they must also have temperature, a notion so bizarre it led Stephen Hawking to discover the radiation that now bears his name. But here's the twist. Unlike your cooling coffee, a black hole's entropy isn't stored in jumbled particles. Instead, the holographic principle suggests it's encoded on the event horizon itself, like data etched onto a cosmic hard drive. Every atom swallowed, every photon consumed, leaves a faint imprint on this boundary, not as recognizable matter, but as microscopic bits of spacetime itself. Critics initially balked at the idea. How could a featureless void store information? Yet string theory and quantum gravity models now offer tantalizing clues. The event horizon might vibrate with unimaginably tiny strings or loops, each oscillation a scrambled fragment of what fell inside. It's as if the universe, unwilling to truly erase anything, found a way to pixelate reality at the smallest possible scale. What makes this so revolutionary isn't just the math, it's the philosophy. Black holes, once seen as the end of information, might actually be its ultimate safeguard. They challenge us to rethink where and how the universe keeps its records. After all, if even the darkest corners of existence preserve data in their own cryptic way, maybe nothing is ever truly lost. Just waiting to be decoded. The next time you hear about a black hole's destructive power, remember, it's not just a cosmic trash can. It's a vault, one with a filing system we're only beginning to understand. And if entropy is any guide, the universe's secrets are far safer than they appear. Echoes from beyond the event horizon. Scientists have long believed that whatever happens inside a black hole stays inside, forever locked behind the event horizon's impenetrable veil. But new discoveries are challenging that assumption, hinting that these cosmic behemoths might be whispering secrets back to us. Strange ripples in space-time, known as gravitational wave echoes, could be the first glimpses of structures inside black holes, structures we were never supposed to see. When black holes collide, they send tremors through the fabric of the universe, gravitational waves that detectors like LIGO and Virgo can pick up. Normally, these signals follow a predictable pattern, a rising crescendo as the black holes spiral toward each other, a sudden chirp at the moment of collision, and then a fading ring-down as the new, merged black hole settles into silence. But something unexpected happens in some of these signals. After the main event, faint, repeating echoes appear, like a cosmic voice bouncing off unseen walls deep within the black hole itself. Theorists have a radical explanation. Instead of a featureless void, a black hole's interior might contain a quantum firewall, a turbulent Planck star core, or even a hidden wormhole throat. If true, the event horizon might not be the smooth, one-way membrane we thought. Instead, it could have microscopic imperfections, tiny bumps or folds that reflect gravitational waves back outward in delayed echoes. These subtle reverberations would carry encoded details about the black hole's deepest, darkest regions. Of course, not everyone is convinced. Skeptics argue these echoes could be noise artifacts from the detectors themselves or unrelated cosmic interference. Yet the tantalizing possibility remains. If these echoes are real, they could rewrite our understanding of black holes entirely. No longer just bottomless pits, they might have internal structure, an architecture hidden from view but detectable in the way space-time itself vibrates. Future observatories like the planned LISA space-based detector could settle the debate with unprecedented precision. For now, these echoes linger on the edge of discovery, a ghostly hint that black holes might not be as silent as they seem. And if we're listening closely enough, they might just reveal what lies beyond the point of no return. Black holes, the universe's most powerful quantum computers. Deep inside a black hole where gravity crushes matter beyond recognition, something astonishing might be happening, an eruption of quantum computation so vast it dwarfs anything we've built on Earth. Forget silicon chips and supercomputers. The singularity itself could be executing calculations at scales we can barely fathom. This isn't just speculative science fiction, it's a serious hypothesis gaining traction among physicists probing the intersection of quantum mechanics and black hole thermodynamics. Imagine the singularity not as a dead end, but as a roiling storm of quantum activity. Every particle, every shred of energy that crosses the event horizon doesn't just vanish, it gets woven into an unfathomably dense tapestry of information processing. Some theories suggest the singularity's extreme environment could act like a quantum circuit, where gravitational and quantum forces interact in ways that process data at speeds we can't replicate. The universe, in this view, might be using black holes as cosmic supercomputers, solving equations too complex for ordinary spacetime. How would this even work? In quantum computing, we manipulate qubits particles that can exist in multiple states at once to perform calculations exponentially faster than classical bits. Now picture a singularity, matter compressed to near infinite density, where quantum fluctuations are magnified to cosmic proportions. The sheer energy and chaos could create a natural quantum processor, with every infalling particle contributing to a computation we can't yet decode. It's as if black holes aren't just devouring information, but transforming it in ways we're only beginning to glimpse. But here's the catch: we'll never see the output. Any data processed inside a black hole is locked away forever. Or is it? Some researchers, like physicist Seth Lloyd, argue that Hawking radiation might carry traces of these computations, scrambled beyond recognition. It's like finding shredded pieces of a cosmic spreadsheet. Theoretically, the information is there, but reconstructing it would require breakthroughs we haven't even dreamed of yet. Not everyone's convinced, of course. Critics counter that calling singularities quantum computers stretches the metaphor too far. Without observable outputs, it's more philosophy than physics. But supporters fire back. If black holes really do preserve information, as quantum mechanics insists, then something must be happening to it. Whether it's computation, encryption, or just cosmic chaos, the singularity isn't just sitting idle. The beauty of this idea isn't just in its audacity, it's in the questions it forces us to ask. Could the universe be running computations on scales we can't perceive? Are black holes not just gravity's masterpieces, but also nature's most alien supercomputers? For now, the answers remain hidden behind the event horizon. But if there's one thing black holes teach us, it's that the universe loves a good puzzle, and this one might be its most exhilarating yet. The invisible thread between black holes and dark matter. For decades, scientists have been piecing together a cosmic jigsaw puzzle, one where most of the pieces are invisible. Dark matter, that mysterious substance outweighing ordinary matter 5-1, refuses to interact with light or any known force except gravity. Black holes, on the other hand, are famously opaque, swallowing light whole. But what if these two enigmas are connected in ways we're only beginning to uncover? One tantalizing hypothesis suggests that primordial black holes, tiny, ancient black holes forged in the chaos of the early universe might be dark matter. Unlike the stellar mass black holes formed from collapsing stars, these relics could be as small as an atom but as massive as a mountain, peppered throughout space like invisible anchors. Their sheer numbers might account for the missing mass that holds galaxies together without emitting a single photon. Here's where it gets speculative. If these primordial black holes exist, their interiors could be hiding something even stranger: exotic particles or quantum fields unlike anything in our standard models. Some theories propose that dark matter isn't just out there but in there, woven into the fabric of black holes themselves. Imagine a black hole's singularity not as a featureless point, but as a knot of dark energy or a vault for unknown particles that only reveal themselves through gravity's pull. Not all physicists are convinced, of course. Critics point out that primordial black holes would leave detectable scars, gravitational lensing events, or radiation bursts that we haven't consistently observed. Others argue that dark matter's smooth distribution in galaxies doesn't quite match the clumpiness expected from a swarm of black holes, but the universe has surprised us before. Whether or not black holes hold the key to dark matter, their potential connection forces us to think differently. If dark matter is tied to these gravitational traps, it would mean the universe's most elusive substance isn't just floating between galaxies. It's lurking in the hearts of the darkest objects we know. And that's a thread worth pulling. The search for answers isn't just about filling textbooks. It's about realizing that the cosmos might be far more interconnected and far weirder than we ever imagined. After all, the best mysteries don't just hide in the shadows, they reshape them. Could black holes be cosmic wombs? Of all the wild ideas in physics, few spark the imagination like this one. What if every black hole is a universe factory? Not just a dead end for matter, but a doorway. The math behind general relativity doesn't forbid it. In fact, some theories suggest that the crushing collapse at the heart of a black hole might not stop at a singularity. Instead, it could rebound, triggering a new Big Bang, an explosion of space-time birthing an entirely separate cosmos. Picture it like this. Our universe could be the offspring of a black hole from another, older universe. And inside every black hole in our cosmos, entirely new universes might be brewing, each with its own laws of physics. Some might have stronger gravity, others no electromagnetism. A fraction could even harbor life. This isn't just poetic speculation, it's a serious hypothesis known as cosmological natural selection, championed by physicists like Lee Smolin. Here's where it gets mind-bending. If these baby universes inherit traits from their parent black holes, say, physical constants slightly tweaked during the bounce, then black holes aren't just accidental monsters. They're evolutionary engines favoring universes that produce more black holes. Over cosmic time, the multiverse could become a fractal tree of realities, each branch fine-tuned for black hole production. Our own universe's hospitable physics, just a happy byproduct of this relentless cosmic replication. But not everyone's sold. Critics argue there's no way to test these ideas, making them more metaphysics than physics. Others counter that the math holds clues like the unnervingly perfect flatness of our early universe, which aligns suspiciously well with what a black hole bounce might produce. And if quantum gravity theories like loop quantum cosmology are correct, singularities might indeed be bridges rather than endpoints. Whether black holes truly birth universes or not, the thought experiment alone is exhilarating. It turns the darkest objects in existence into creative forces, cosmic seeds scattered across the multiverse. And if even a fraction of this is true, then every galaxy center Leviathan might not just be a destroyer, but a creator hiding entire worlds beyond its veil. After all, nature rarely wastes a good catastrophe. Why should black holes be any different? Black hole starships, the ultimate cosmic engines. Picture this. A starship not powered by rockets or solar sails, but by the most destructive force in the universe, a tamed black hole. For a civilization advanced enough to harness such power, black holes could become the ultimate engines, propelling ships across the galaxy at speeds we can barely fathom. It sounds like science fiction, but the physics behind it is shockingly plausible. The concept hinges on two cosmic cheat codes: Hawking radiation and gravity's relentless pull. A microscopic black hole, just a few atoms wide but weighing as much as a mountain, could emit Hawking radiation at staggering temperatures, millions of degrees. Capture that energy, and you've got a power source dwarfing anything nuclear or antimatter could offer. The numbers are mind-blowing. A 1-ton black hole could generate petawatts of energy, enough to light up entire worlds. But propulsion is where things get truly wild. Instead of fighting gravity, a black hole starship might ride it. One theoretical design, called the Penrose process, involves dropping matter into a spinning black hole's ergosphere, a region just outside the event horizon where spacetime itself gets dragged into a whirlpool. By carefully aiming the debris, you could steal rotational energy from the black hole, shooting your ship forward like a slingshot, efficiency near perfect. Speed limited only by how close you dare to dance with the abyss. Of course, the engineering hurdles are daunting. Creating or capturing a stable black hole, let alone keeping it aboard your ship, would require technology light years beyond ours. A miscalculation could turn your warp drive into a cosmic grenade. Yet for a type Roman II or Roman III civilization, one that commands the energy of stars or galaxies, this might just be the ticket to galactic dominance. The beauty of this idea isn't just in its audacity, but in its reminder: the universe's most fearsome phenomena might also be its greatest gifts. Black holes don't just destroy, they transform. And if humanity ever reaches for the stars, we might find our best engines were hiding in the darkest corners of space all along. The invisible frontier. Why black holes keep their secrets. Peering into a black hole isn't just hard, it's like trying to read a book that's been set on fire. These cosmic enigmas actively erase the very tools we rely on to study them. Light can't escape their pull, matter vanishes without a trace, even space-time itself twists into knots. So how do we probe the unknowable? The first hurdle is simple. Black holes are, by definition, invisible. Without light or any radiation escaping from beyond the event horizon, traditional telescopes hit a wall. We can't photograph what doesn't emit or reflect a single photon. Instead, scientists rely on indirect clues like the frenzied dance of stars orbiting unseen giants, or the X-ray screams of superheated gas spiraling toward oblivion. Instruments like the Event Horizon Telescope, which captured the first shadow of a black hole in 2019, don't see the hole itself, they map the absence of light where the event horizon blocks background radiation. But the deeper challenge lies in time. Near a black hole's edge, gravity warps clocks as much as it warps space. To an outside observer, anything crossing the horizon appears frozen in time, its image redshifted into oblivion. Imagine watching a probe descend toward a black hole. Its signals would stretch into longer, dimmer wavelengths until they fade entirely, like a radio station lost to static. By the time we see it touch the edge, the probe's fate was sealed millennia ago from its own perspective. Quantum mechanics adds another layer of frustration. Heisenberg's uncertainty principle dictates that the more precisely we try to pinpoint a particle near the event horizon, the more violently its energy fluctuates. It's like zooming in on a digital image until it dissolves into pixelated chaos. Even in theory, there's a fundamental limit to how much we can see before the rules of reality blur. Yet astronomers aren't entirely blind. Gravitational wave detectors like LIGO listen for the ripples produced when black holes collide, a cosmic percussion that reveals their masses and spins. Future missions like the planned LISA Space Observatory could detect even fainter tremors, potentially uncovering echoes from behind the event horizon. Some theorists also hope quantum entanglement's spooky action at a distance might one day offer backdoor insights, though that remains speculative. The irony is stark. Black holes may be the universe's most extreme laboratories, but they're also locked rooms with the keys thrown away. Every breakthrough peels back a layer only to expose deeper mysteries. For now, studying them is like reconstructing a symphony by listening to the silence between the notes. But as technology races to catch up with theory, even the darkest corners of existence might not stay hidden forever. After all, the universe loves a challenge, and so do we. Simulating the unseeable. When supercomputers meet black holes, try building a model of something that actively destroys every tool you'd use to study it. That's the paradox of simulating black holes. Yet scientists are doing exactly that, pushing supercomputers to their limits to recreate conditions no telescope could ever observe. These digital laboratories don't just mimic black holes, they stress test our wildest theories about what happens where physics breaks down. The challenge starts with scale. To simulate a black hole's interior, you need to account for both Einstein's universe-bending gravity and the subatomic chaos of quantum mechanics, two rulebooks that famously clash. Supercomputers like NASA Discover or the Blue Waters system tackle this by dividing the problem into layers. Imagine rendering a video game where every pixel follows different physics. One moment, you're calculating the smooth curvature of space-time near the event horizon. The next, you're tracking quantum particles flickering in and out of existence at the singularity's edge. Some simulations focus on the visible drama, like two black holes colliding, their mergers now detectable thanks to gravitational wave observatories. Others venture into the unseen, probing hypothetical structures like wormholes or Planck stars hidden behind the horizon. In 2021, a team at the University of Illinois used modified Einstein equations to simulate a singularity-free black hole, revealing how quantum effects might halt infinite collapse. The result, a turbulent but finite core that rebounds like a spring no cosmic shredder required. But here's the catch, even the most powerful supercomputers can't simulate a black hole perfectly. The calculations are so complex that shortcuts are inevitable. Some models approximate quantum gravity by treating spacetime as a pixelated grid. Others ignore Hawking radiation entirely to focus on gravitational tides. It's like reconstructing a symphony by only listening to the bass line. You get the gist, but nuances are lost. Yet every flawed simulation teaches us something. When digital black holes spit out unexpected echoes or stabilize wormholes in ways math alone couldn't predict, it hints at possibilities lurking in nature's blind spots. These aren't just video game fantasies, they're stress tests for reality itself. And as computing power grows, so does our ability to ask the universe, is this how you really work? For now, the simulations are messy, incomplete, and endlessly debated. But they're also our best shot at decoding the cosmos' darkest riddles, one line of code at a time. The next frontier, tuning into black holes' hidden symphony. For centuries, black holes were silent phantoms, their existence inferred only by the way they warped the cosmos around them. But we're on the verge of a revolution, one where cutting-edge technology could finally let us listen to their deepest secrets. The key, a new generation of gravitational wave detectors so precise, they might pick up whispers from inside the event horizon. Imagine trying to study a locked vault by feeling the vibrations in its walls. That's essentially what scientists are doing with tools like LIGO and Virgo, which detect ripples in spacetime when black holes collide. But current detectors are like using a stethoscope to hear a concert through concrete, helpful but limited. Upcoming missions like the Laser Interferometer Space Antenna LISA, set to launch in the 2030s, will change the game. By placing detectors millions of kilometers apart in space, free from Earth's seismic noise, LISA could catch frequencies 1,000 times lower than LIGO, potentially revealing the faint echoes of black holes merging behind the veil of an event horizon. But it's not just about bigger detectors. Quantum squeezing technology, already being tested at LIGO, manipulates light at subatomic scales to reduce interference, making the instruments exponentially more sensitive. Think of it like tuning out static to hear a faint radio station, except the station is a pair of black holes spiraling toward collision 13 billion years ago. Some theorists are even more ambitious. Proposals like the Einstein telescope, a next-gen underground observatory, aim to detect not just the thunderous crashes of massive black holes, but the delicate chirps of tiny primordial ones. These ancient relics, no wider than an atom but as heavy as a planet, could be hiding in our cosmic backyard if we can just build sensitive enough tools to spot them. The ultimate prize, catching the elusive gravitational wave echo, a faint, repeating signal that could hint at structures inside a black hole, like a Planck star's quantum core or the turbulent throat of a wormhole. It's a long shot, but as physicist Kip Thorne once said, "The universe is under no obligation to make sense to us, but we're under every obligation to keep listening." What makes this era thrilling isn't just the tech, it's the philosophy. For the first time, we're not just staring at black holes from a safe distance. We're building instruments that might finally let us peek through the keyhole. And if the universe cooperates, the next decade could rewrite astrophysics textbooks in ways we can't yet imagine. After all, the cosmos rarely reveals its secrets easily, but with a little ingenuity and a lot of patience, we might just crack the code. Playing with cosmic fire, the ethics of black hole manipulation. Black holes have always been the universe's untouchable enigmas, but what if we could touch them? As our technology edges closer to deciphering their secrets, we're forced to confront a dilemma. Just because we can interact with these cosmic monsters, should we? The ethical stakes are as vast as the voids themselves. Take the idea of harvesting energy from black holes. Theoretically, a civilization advanced enough could mine Hawking radiation or exploit a spinning black hole's ergosphere for near-limitless power. But the risks are apocalyptic. One miscalculation could destabilize the black hole's orbit, sending it careening toward populated star systems, a runaway cosmic bulldozer. Even if we avoid catastrophe, would harnessing such forces make us custodians of the universe or its next great destabilizers? Then there's the question of experimentation. Suppose we someday create artificial micro-black holes in labs, as some quantum gravity models suggest might be possible. The potential for scientific leaps is enormous, but so are the nightmare scenarios. A containment failure could see Earth devoured from the inside out in seconds. The same curiosity that fuels breakthroughs could also become an existential threat. And what of the universe's natural order? Black holes aren't just objects, they're cosmic regulators, shaping galaxies and recycling matter across eons. Tinkering with them might disrupt balances we don't even fully understand. It's like removing a keystone from an arch. We might not notice the damage until the entire structure collapses. But the most haunting question isn't about physics, it's about hubris. If black holes truly hold gateways to other universes or store encrypted cosmic history, do we have the right to manipulate what might be another realm's foundation? Indigenous cultures often speak of sacred spaces where human interference is forbidden. Could black holes be the universe's version of those sanctuaries? These aren't just hypotheticals. As we inch toward becoming a spacefaring civilization, the line between exploration and exploitation blurs. The answers won't come from equations alone. They'll require something far rarer in science: wisdom. Because some doors, once opened, might not close again, and behind them could lie wonders or warnings we weren't meant to ignore. The cosmic mirror, how black holes shatter our perception of reality. Black holes don't just bend space-time, they twist our deepest assumptions about existence itself. These cosmic anomalies force us to confront questions that blur the line between physics and philosophy. What is real? Can information truly vanish? And if the laws of nature break down inside a singularity, does the universe have fundamental rules at all, or just temporary guidelines? Consider the fate of an object falling into a black hole. From an outside observer's perspective, it never crosses the event horizon, just fades into an eternal freeze frame like a bug trapped in amber. But for the object itself, time flows normally as it plunges inward. So which version of events is real? Relativity insists both are valid, revealing an unsettling truth: reality isn't absolute. It's fractured, dependent on who's watching and from where. Black holes expose the universe as a cosmic hall of mirrors where even basic truths become elastic. Then there's the information paradox. Quantum mechanics claims the universe never forgets, every particle's history is preserved. But black holes seem to erase data with impunity, crushing the universe's ledger into a singularity. Unless, as holographic theory suggests, that information is smeared across the event horizon like a cosmic backup drive. Either way, these contradictions force us to rethink whether existence requires permanence, or if reality is more like a temporary arrangement of quantum probabilities, constantly rewriting itself. Philosophers have wrestled with such questions for millennia, but black holes make them urgent. If space and time can be warped beyond recognition, do they have any intrinsic meaning, or are they just flexible tools the universe uses to organize chaos? Even causality, the bedrock of science, wobbles near a singularity. Events might not unfold in tidy sequences of cause and effect. Time could loop, fracture, or cease altogether. The most humbling realization: black holes might not be cosmic glitches. They could be proof that our understanding of reality is hopelessly limited, like ants trying to map a hurricane. Every breakthrough, from Hawking radiation to quantum hair, feels like peeling back a layer of an infinite onion. We're left staring into the abyss, wondering if the universe is fundamentally unknowable, or if we're just missing the right vocabulary. Perhaps that's the gift of these gravitational riddles. They don't just challenge science, they redefine what it means to ask a question. After all, if reality itself is negotiable, the only limit is our courage to keep probing the darkness. Black holes in pop culture. When Hollywood meets astrophysics for decades, black holes have been more than cosmic oddities. They're storytelling goldmines. From blockbuster movies to best-selling novels, pop culture has taken these gravitational monsters and spun them into everything from time machines to cosmic horror. But how much of what we see on screen aligns with the real science? Let's sift through the fiction to find the fascinating grains of truth and the wild liberties artists love to take. Take Interstellar, one of the most ambitious attempts to blend science with spectacle. Its black hole, Gargantua, was meticulously designed with physicist Kip Thorne's guidance, resulting in the first ever accurate depiction of gravitational lensing, the way a black hole distorts light around it. The film even got the time dilation effect eerily right, with 1 hour on Miller's planet costing years back on the ship. But then there's the Tesseract sequence inside the black hole, a poetic, abstract twist that trades realism for emotional storytelling. Science says you'd be spaghettified long before reaching the interior. Hollywood says, what if love transcends dimensions? Then there's Event Horizon, which throws realism out the airlock entirely. Here, a black hole isn't just a gravity well. It's a literal gateway to hell, complete with haunted spaceships and gory hallucinations. While the movie leans into pure horror, it taps into a real scientific debate. Could black holes connect to other universes? The answer is probably not, but the film's nightmare fuel resonates because it exploits our primal fear of the unknown, something astrophysicists grapple with in their own way. Books often fare better. The Three-Body Problem trilogy treats black holes as strategic tools, cosmic billiard balls for advanced civilizations. Andy Weir's Project Hail Mary imagines microscopic black holes as power sources, a nod to real theories about Hawking radiation. Even Doctor Who plays with the idea of black holes as prisons for eldritch monsters. blending folklore with theoretical physics in a way that's cheeky but weirdly thought-provoking. Video games like No Man's Sky and Destiny turn black holes into fast travel portals, glossing over the messy death by tidal forces part. Meanwhile, Elite Dangerous leans harder into realism. Fly too close and your ship gets torn apart by gravitational shear. It's a rare moment where gameplay aligns with the brutal reality. Black holes don't care about your warp drive. The takeaway: pop culture's black holes are like funhouse mirrors, distorted but reflecting glimmers of real science. Filmmakers and writers aren't bound by equations, and that's okay. Their job is to thrill, terrify, or move us, even if it means bending space-time into a plot device. But the next time you see a character survive a black hole unscathed, just remember, in reality, the universe doesn't do happy endings, at least not without a little creative physics. And who knows, maybe one day the wildest sci-fi ideas, wormholes, quantum tunnels, cosmic rebirth, will find footing in real theory. Until then, enjoy the spectacle. Just don't test it in person. Beyond the event horizon, the universe's greatest unsolved riddle, we've journeyed through the mind-bending theories, spaghettification, singularities, holographic information, even baby universes hidden in the abyss. Yet the more we uncover about black holes, the clearer it becomes. These cosmic enigmas are the universe's way of humble bragging. You think you've figured me out? Try this. Every answer leads to deeper questions, every theory a doorway to paradoxes we're still learning to articulate. Take the singularity. Physics paints it as a point of infinite density where the rulebook burns to ashes, but is it truly a dead end or a portal we're too primitive to recognize? Some models suggest quantum gravity might smooth that sharp edge into a Planck star's rebound. Others whisper of wormholes threading through space-time like cosmic subway tunnels. Then there's the holographic principle, turning black holes into cosmic hard drives where 3D reality is just a projection from a 2D surface. The math works. The implications mind-melting, and let's not forget Hawking radiation, the slow leak that could erase black holes entirely, unless, of course, their secrets are encoded in those fading whispers after all. Even the event horizon, that perfect one-way membrane, might be fuzzier than we thought, bristling with quantum hairs or hiding firewalls that crisp intruders on arrival. The debate rages on because when it comes to black holes, certainty is the rarest commodity in the cosmos. Here's the exhilarating truth: we're standing at the edge of a cosmic frontier. Black holes don't just defy our understanding, they expand it, forcing us to rewrite physics in real time. Every observation from gravitational wave echoes to the eerie glow at galaxy centers, chips away at the unknown. But for every puzzle solved, 10 more emerge, each more tantalizing than the last. So stay curious. The universe isn't done surprising us, and neither are we. If today's wildest theories sound like science fiction, just wait, tomorrow's breakthroughs might make them textbook chapters. Until then, keep gazing into the abyss. Sometimes it gazes back with answers. If you love diving into the cosmos' deepest mysteries, don't miss out on what's next. Hit subscribe and let's keep unraveling the universe one black hole at a